In the last lecture, we defined the integral of a continuous function defined on the image of a curve gamma. We defined the integral to be the limit of the Riemann sums over all partitions as the partition size goes to 0, and we did prove that the limit does exist, and we called that the limit of f over gamma, denoted it as integral of f of z dz over gamma. We also discussed some of the properties of this integral. So, in this lecture, we will study the complex analog of the fundamental theorem of calculus, rather the first fundamental theorem of calculus. Let me write down the setting and begin the lecture. So, we will be discussing the first fundamental theorem of calculus. In a course on real analysis, you would have seen a version of the first fundamental theorem of calculus. What did the first fundamental theorem of calculus in real analysis tell us? It told us that if there is a function small f such that capital F is an antiderivative, or rather capital F prime of z is equal to small f of z, then the integral of f of z over from a to b, where it is all these are defined over ab, is equal to capital F of b minus capital F of a. The complex analog is quite similar. Let me write down the statement and then we will discuss about that. So, theorem. Let omega be an open subset of C and f from omega to C be a continuous function. And now we will have to talk about the existence of an antiderivative. Let capital F from omega to C be an antiderivative. What does it mean to say that capital F is an antiderivative of small f? I.e., our function capital F is holomorphic on omega to begin with. Not only is it holomorphic, but its complex derivative at each point is equal to small f of z. I.e., capital F is holomorphic on omega and capital F prime of z is equal to small f of z for all z in omega. So, this is the meaning of capital F being an antiderivative of small f. So, what is the fundamental theorem of calculus going to tell us? Suppose gamma is a rectifiable curve. Defined in omega. That means that gamma from AB to C is a curve such that gamma of AB is sitting inside omega, is contained in omega. Suppose gamma is a rectifiable curve defined on omega, then the integral of f of z dz over gamma, this is equal to f of z1 minus f of z0, where z0 is the initial point of gamma, or rather gamma of A, and z1 is the terminal point of gamma, or in other words gamma of B. So, the complex analog is, as one would expect, it's capturing a statement very similar to the one in real analysis. Let's give a proof. Let's begin the proof by observing that we have only imposed the condition here that our curve gamma is rectifiable. So, if you recall from the previous lecture, if we put more regularity assumptions on our curve gamma, we will be able to get a better or an easily workable form of integral of f of z dz. In particular, let me write that part down. Suppose our curve gamma is having more regularity. Suppose gamma is continuously differentiable. Then what do we have? Then let's recall the change of variable formula that we had proved in the last lecture. Then integral of f of z dz over gamma, this is going to be equal to integral from a to b, the usual Riemann integral applied to the real part and the imaginary part of f of gamma of t, gamma prime t dt. We can write our integral in this manner. If the function capital F is, if the curve gamma is a continuously differentiable curve. And now let us apply the fact that capital F is an antiderivative. Since f prime of z is equal to f of z for all z in omega, integral of f of z dz over gamma, this is going to be equal to integral a to b capital F of gamma of capital F prime of gamma of t, gamma prime of t dt. Now, by invoking the chain rule, I'll just put it as an exercise for you to sit down and check that by the chain rule, along with the Cauchy-Riemann equations applied to capital F, by the chain rule and CR equations. This chain rule I am talking about is the chain rule in higher dimensions, which I will assume from a course on real analysis in several variables. This is going to be equal by chain rule f prime of gamma of t. Remember that f prime is the complex derivative of f, capital F, gamma prime t is equal to f composed with gamma prime t dt. And therefore, integral of f of z dz over gamma is just going to be equal to integral of f composed with gamma prime t dt, and this can be now deciphered by using the first fundamental theorem of calculus proved in the real analysis setting, which will tell us that this is equal to f of gamma of b minus f of gamma of a, which is equal to f of z1 minus f of z0. So, if the curve gamma is continuously differentiable, our work becomes extremely easy, and we will be able to conclude the fundamental theorem of calculus, the complex analog rather, from the fundamental theorem of calculus proved in the real analytic setting, in the real analysis setting. However, we have put more generality here. We are only assuming that our curve is rectifiable, and therefore we will not have this expression in general. So, we will have to work a bit more to prove our result in the complex analog case. So, we will prove the result for rectifiable curves by using the connectedness of the compact set AB, where the curve gamma is defined. So, let us start by defining the set omega epsilon. So, given epsilon positive, or maybe u epsilon, given epsilon positive, let u epsilon be the collection of all those t in AB, such that when you restrict the curve gamma from A to T, then the fundamental theorem of calculus is satisfied up to an error term given by epsilon. So, let me just write down what that means. Let u epsilon be the set of all t such that the integral from A to T of f of z dz minus f of gamma of t minus f of gamma of a, this absolute value is less than epsilon times the arc length of gamma restricted to at. So, let us look at the set epsilon, or maybe I should be a little more careful. This is satisfied for all a less than or equal to t0 less than or equal to t. So, here as well I should be a little more careful. This is less than or equal to epsilon times the arc length of gamma restricted to a comma t naught for all a less than or equal to t naught less than or equal to t. We will prove that the set u epsilon is both open and closed at the same time, and since small a belongs to u epsilon, it is non-empty as well, and by invoking the connectedness of the closed interval AB, we will be able to conclude that U epsilon is equal to the entire closed set AB. And our choice of epsilon is arbitrary, and because of that we will be able to get that integral from a to b of f of z dz, and f of gamma of b minus f of gamma of a are arbitrarily close, and then we would be done. So enough to show that U epsilon is both open and closed. Let's prove that it is closeness. So let t0 be a limit point of omega epsilon. That means there exists Tn converging to T naught, where Tn are elements in omega epsilon. So the first observation is that if Tn is greater than T naught, then we are done. Then T naught is automatically in omega epsilon, because if T is in omega epsilon, all T prime less than or equal to T will also be in epsilon. That is how the definition of epsilon, omega epsilon is. And because of that, we can assume that Tn is a sequence converging to T naught from below. Hence, we may assume Tn converges up to T naught. Okay, so if you now notice what is f of z dz over gamma restricted to a comma t naught minus f of gamma of t naught minus f of gamma of a. Let's look at this. This absolute value, this is equal to the integral of f of z dz of gamma restricted to atn plus gamma restricted to tn comma t naught. So this is the concatenation of the curves gamma restricted to atn and the curve gamma restricted to tn comma t naught. Now here we will introduce a couple of terms, t naught minus f of gamma of tn plus f of gamma of tn minus f of gamma of a. And by the properties of the complex integral we have already discussed, this is just going to be equal to the absolute value of integral of f of z dz of gamma over gamma restricted to a comma tn minus f of gamma of tn minus f of gamma of a. Maybe I should change this equality by triangle inequality. This will be less than or equal to the first term being this plus the absolute value of integral gamma restricted to tn comma t naught of f of z dz minus f of gamma of t naught minus f of gamma of tn. Now, since Tn belongs to the set omega epsilon, remember what U epsilon was. Okay, so I used an omega epsilon here. Maybe I should change it here to omega epsilon so that it will be consistent. Yeah. So if Tn belongs to omega epsilon, then by the very definition, this condition is satisfied by Tn. That means that the first term is bounded by epsilon times the arc length of gamma restricted to a comma tn. And how about the second term? Now the second term we can say that is less than or equal to some capital M. F is a continuous function on the on the image of gamma of AB, which is a compact set, and therefore it's always bounded above by some capital M, and by again using one of the integral from gamma restricted to Tn comma T naught minus capital F, or this is less than or equal to this, plus absolute value of capital F of gamma of T naught minus gamma of Tn. Now the function capital F is holomorphic on omega. In particular, it is continuous. It's continuous at every point of omega, and in particular, it's continuous at T naught. So by picking Tn arbitrarily close to T naught, and by using the uniform continuity of gamma, we can ensure that this term can be made less than any delta that we would like to have. So let me just write it down. Given an epsilon prime positive, we can pick, I leave the details to you, Tn arbitrarily close to T naught such that this is less than or equal to epsilon times the arc length of gamma restricted to Tn plus m times epsilon prime, or rather m plus 1 times epsilon prime, some constant times epsilon prime. So we given any epsilon prime, we will be able to make it as small as we want. But then what were we estimating? We were estimating the term this. This was the term we were estimating. So let me just write that down again so that we know exactly what we were doing. Hence, what do we have? The absolute value of integral of f of z from a to T naught. This minus f of gamma of T naught minus f of gamma of A. This is less than or equal to epsilon times the arc length of gamma restricted to A comma Tn plus m plus 1 times epsilon prime. And this is true for every epsilon prime that we can. So this tells us that the quantity here is in particular less than or equal to epsilon times the arc length of gamma restricted to A comma Tn, which hence is less than or equal to epsilon times the arc length of gamma restricted to A comma T naught. And that's precisely what we had set out to prove. And therefore, T naught belongs to omega epsilon, and hence omega epsilon is closed. Omega epsilon is the name we have given. I just changed the name from u epsilon to omega epsilon. So let me stick to the omega epsilon. Right now, omega epsilon is a subset of the interval AB, and it shouldn't be confused as being a subset of omega, even though I use the notation omega epsilon. All right, let us now prove that omega epsilon is an open subset as well. So the next claim is to prove that omega epsilon is open. So notice that we have still not used the fact that capital F is a holomorphic function. We will prove that if T naught is now a point in omega epsilon, we will prove that T naught is an interior point. And in order to do that, we will use the fact that capital F is complex differentiable at the point gamma of T naught. So let's prove that T naught, any point T naught in omega epsilon, is going to be an interior point. So let T naught be, and that would prove that omega epsilon is open. Now, if T prime is less than T naught, then T prime is already in an element of omega epsilon. And because of that, for any delta such that T naught minus delta to T naught plus delta is contained in capital AB, T naught minus delta to T naught is already in omega epsilon. So let me just note that for delta positive such that T naught minus delta to T naught plus delta is contained in omega contained in AB, we have T T naught minus delta to T naught, this set is contained in omega epsilon by the very definition of omega epsilon. So we'll just prove that for T in T naught to T naught plus delta, where our delta is yet to be picked, we will prove that all the points here belong to omega epsilon. That is the goal. And in order to do that, let us use the fact that capital F is holomorphic at the point gamma of T naught. Since F is holomorphic at gamma of T naught, given epsilon positive, maybe we will change this epsilon later according to our requirement. Let's see. Given epsilon positive, there exists a delta such that the Newtonian sums capital F of gamma of T minus the capital F of gamma of T naught by gamma of T minus gamma of T naught. This is arbitrarily close to epsilon, close to the derivative of capital F, which is small f, which we know is small f. This is less than epsilon. Maybe let's put a by 2 if needed. We'll correct it later. Whenever T belongs to T naught comma, okay, let me not include T naught comma T naught plus delta. So this can be arranged by using the holomorphicity or complex differentiability of capital F at T naught. And rewriting this, what do we have? Then absolute value of capital F of gamma of T minus capital F of gamma of T naught minus F of gamma of T naught into gamma of T minus gamma of T naught. This is less than or equal to epsilon by 2 times the absolute value of gamma of T minus gamma of T naught. Now let's focus on the term here. F of gamma of T naught times gamma of T minus gamma of T naught. This is exactly equal to the integral of F of gamma of T naught dz, where the integral is restricted to T naught comma T. Remember that T is greater than this. Let me remind you that T naught is a element in the open interval T naught to T naught plus delta. Let us now use the uniform continuity of F composed with gamma to pick delta sufficiently small. Let delta be small enough. If it is not small enough, make it smaller so that the absolute value of F of gamma of T minus F of gamma of T naught, this is less than, say, epsilon by 2. Then what do we have? Then the integral of F of z dz over gamma restricted to T naught comma T minus the absolute value of this F of gamma of T naught times gamma of T minus gamma of T naught. If you look at the quantity, this absolute value, remember that this thing on the right is exactly what we have here. So we are estimating that term here, and that can be estimated in the following manner. This is going to be less than or equal to the integral of the absolute value of F of z minus F of gamma of T, rather T naught dz over gamma restricted to T naught comma T, and we know that this is less than or equal to epsilon by 2 times the arc length of gamma restricted to T naught comma T. Okay, so let's get back to what we were proving. This is going to be equal to, by using the triangle inequality now here, we apply the triangle inequality here. and so we now have an estimate on the integral of f dz restricted to gamma t naught comma t. We also we know how close to f of gamma of t naught times gamma of t minus gamma of t naught is. We also have estimated capital F of gamma of t minus capital F of gamma of t naught. So notice that this is in particular less than or equal to epsilon by 2 times the arc length of gamma restricted to t naught comma t. And the integral here, both are estimated by f of gamma of t naught times gamma of t minus gamma of t naught to this order. So let me now write down by using triangle inequality. Hence, by triangle inequality, we have, by adding and subtracting the terms, integral of f of z dz over gamma restricted to t naught comma t minus f of gamma of t minus f of gamma of t naught. This term is approximated by epsilon times gamma restricted to t naught comma t. Notice that the epsilon by 2 was picked precisely for that. There is this epsilon by 2 and there is this epsilon by 2. Both of them will contribute to the epsilon here. Alright, so we are now in good shape because we now only need to add the corresponding equation for T naught. So we know that since T naught belongs to omega epsilon, we have the integral of f of z dz of gamma a restricted to a comma t naught minus f of gamma of t naught minus f of gamma of a. This is less than or equal to epsilon times the arc length of gamma restricted to a comma t naught. And let's call this star, let's call this. So notice that integral of f of z dz over gamma restricted to a comma t is equal to the integral of f of z dz over gamma restricted to a comma t naught plus gamma restricted to t naught comma t, the concatenation of these two curves. And also by introducing this term, we can finally conclude by using the triangle inequality. Hence, gamma restricted to a comma t of f of z dz minus f of gamma of t minus f of gamma of a. This is less than or equal to epsilon times the arc length of gamma restricted to a comma t naught plus epsilon times the arc length of gamma restricted to t naught comma t. And we know that the arc length of gamma restricted to a comma t is going to be equal to the sum of the arc length of gamma restricted to a comma t naught plus the arc length of gamma restricted to t naught comma t, which is in particular equal to epsilon times gamma restricted to a comma t. And this is precisely what we had set out to prove. This is true for all t in t naught to t naught plus delta. Which implies that t naught minus delta to t naught plus delta is contained in omega epsilon. Hence, omega epsilon is open. It means that it is both open and closed and contains A. We have, by connectedness of AB, omega epsilon is equal to A comma B. So let's recall what it means to say that omega epsilon is equal to a comma b. It means that integral of f of z dz over gamma minus f of gamma of b minus f of gamma of a. This absolute value is less than or equal to epsilon times the arc length of gamma. Gamma restricted to a comma b is exactly equal to the arc length of gamma. But our choice of epsilon was arbitrary. This is true for all epsilon positive. We have concluded this. That tells us that because our choice of epsilon was arbitrary, f of z dz is equal to f of z1 minus f of z0, where z1 is equal to gamma of b and z0 is equal to gamma of a. And this is precisely what we had set out to prove. So even in the case when our curve gamma is rectifiable, we do have the fundamental theorem of calculus, the first fundamental theorem of calculus. The first fundamental theorem of calculus is quite powerful in the sense that it helps us in computing the integral of functions whose antiderivative is already known over rectifiable curves. So let us look at some of the nice applications of the first fundamental theorem of calculus. So we know that so this is completed, that e to the power d by dz of e to the power z is equal to e to the power z. That means e to the power z is the antiderivative of e to the power z in the whole complex plane. Hence, integral of e to the power z dz over any curve gamma is just going to be equal to e to the power z2 minus e to the power z1, where gamma is a curve. So these are examples. Is a curve from z1 to z2. So I am being a little casual by saying that it is a curve from z1 to z2. It means that it is a rectifiable curve with initial point z1 and the terminal point z2. Let's now look at another example. We know that d by dz of z square is equal to 2z, or rather half z square by 2 is equal to z. Applying the fundamental theorem of calculus over any curve gamma of z dz, this is going to be equal to z1 square minus z2 square by 2, where as earlier z1 is initial point, or maybe I should be a little careful. Now I made it z1 and z2 rather than z0 and z1, but yeah, it's quite straightforward, no confusion will come up. So these were entire functions. Let's look at some function which is not an entire function. On c minus 0, we have d by dz of 1 by z to be equal to, okay, so let me put a minus already here. Minus of 1 by z is equal to 1 by z square. Now let's look at the integral of 1 by z square dz over some curve gamma. We know that its antiderivative is equal to minus of 1 by z. So this is going to be minus of 1 by z2 minus 1 by z1. This is precisely what we will be getting. Let's now consider some power series in its domain of definition. Let summation a n z minus z0 be a power series converging in dz0 r. So that means r is the radius of convergence of this power series. So this is capital F. Let g of z be equal to summation to the power n. Summation a n by n plus 1 into z minus z0 to the power n plus 1. And we have g prime is equal to g prime of z is equal to capital F of z. By applying the fundamental theorem of calculus, we have integral of summation an z minus z0 to the power n dz over gamma. This is just going to be equal to the antiderivative being a. So since it converges at these points, this will also on dz0r by the way. This is going to be equal to summation an times z1 minus z0 to the power n by n plus 1 minus z2 minus, or rather z2 minus z0 to the power n plus 1 minus z1 minus z0 to the power n plus 1 by n plus 1. So we have crucially used the fact that this series converges on every point of dz0r to write it like this. Okay, so let me stop here.